Good morning everyone. I am Tanushree Dalai from Civil Engineering branch and today I am going to teach you your Theory 2 paper which name is Structural Design 2. So in the last class we did a numerical based on tension member and this numerical is based on the plate section. And today we will discuss another numerical which based on the plate section of tension member. So here is your question, which is a flat size 200 mm into 10 mm of grade Fe410 used as tension member is connected to a 12 mm gusset plate as shown in the figure. Calculate the strength in yielding, rupture and block shear, and the bolt is given as 20 mm dia which is a property class of 4.6. So here is your diagram. This is your flat member or plate member and this is your gusset plate. The size of the plate is 200 mm into 10 mm and the thickness of the gusset is 12 mm. The plate is connected to the gusset by 6 numbers of bolt of dia 20 mm and the pitch distance is given as 60 mm and the edge distance is given as 40 mm. Okay. So now comes to the solution part. So first of all, the data given. So here in the question it is given as the grade of the steel is Fe410, so that the ultimate strength of the steel is given as 410 Newton per mm square or megapascal and yield strength is given as 250 Newton per mm square. Then gamma m0, which is the partial safety factor for the plate, is given as 1.1. Then gamma ml, which is the partial safety factor for the bolt, is given as 1.25. Then for the 20 mm dia of the bolt, the diameter of the hole is given as 22 mm. And again another partial safety factor for the bolt is given as 1.25. All the partial safety factors are from the table number 5 in IS code 800/2007. So now the first strength calculation, which is the strength of the plate against yielding. So this formula is for use to calculate the strength of the plate against yielding, which is TDG equal to Ag into Fy divided by gamma m0. So now Ag is the gross area section of the plate section. So we know that the dimension of the plate is given as 200 into 10. So Ag is calculated as B into T. That means width of the plate into thickness of the plate. So width of the plate is given as 200 and thickness of the plate is given as 10. So B into T multiplied by Fy, which is 250 for Fe410 and gamma m0 equal to 1.1. So by calculating all this value, we got 454.55 kilonewton. Okay, so 454.55 kilonewton is the strength of the plate against the yielding. So now comes to the next strength calculation, which is strength of the plate against rupture. So for the rupture case, in the plate section, the formula is TDN equal to 0.9 FUAN divided by gamma ml. So we know the value of Fu, we know the value of gamma ml. So we just calculate the AN value, which is the net effective area of the plate section. So to calculate the AN value, we have a formula which is B minus ND0 whole multiplied by T. So B is the width of the plate, and here N is the numbers of bolt in critical section, and D0 is the diameter of the hole, and T is the thickness of the plate. So to calculate the numbers of bolt in critical section, we have to see the diagram. So here you see the number of critical section means if we draw a vertical section along the plate, then how many numbers of bolts are there? That is the numbers of bolt in the critical section. So here the 6 numbers of bolt is provided in 2 rows. So here is one row and here is another row. So now if we draw a vertical section along the plate by which the numbers of bolt is cut out in the perpendicular direction to the plate section, then you see here 2 numbers of bolt are there. Then here also 2 numbers of bolt are there. Then again here also 2 numbers of bolts are there. So we can say that the numbers of bolt in each critical section is 2. Okay. So now put the value in this formula. So B is your 200 mm. Numbers of critical bolt numbers is 2 numbers. And the diameter of the hole is 22 and thickness of the plate section is 10. So by calculating this value, we got 1560 mm square. So now put this value in the TDN formula. So 0.9410 into 1560 divided by 1.25 equal to 460.51 kilonewton. So 460.51 kilonewton is the value of strength of the plate against rupture. So now comes to the third part of the strength calculation in the plate section, which is block shear strength of the plate section. So the block shear strength of the plate section is calculated by 2 numbers of formula. So first one is your TDB1 and second one is your TDB2. So here to calculate this 2 value, we have to calculate the AVG value, ATN value, ATG value and AVN value. So first of all, we have to calculate these 4 area for the block shear portion of the plate section. So now you see here, this is your plate section and this plate section is connected by 6 numbers of bolt. So now the block shear portion will be along this line and again it cut out by vertically here and again it horizontally cut out up to this. So this portion is known as your block shear portion. Okay. So this portion is your block shear portion. So this small section we will draw in maximize here so that we can easily calculate the value of all the area. Okay. So now let us assume the horizontal line of the block shear portion is V line and the vertical line is known as your T line. Okay. So now when we calculate the AVG and AVN value, we have to consider this to this portion. Okay. And when we will calculate the ATG and ATN value, then we have to consider the vertical portion of the block shear. Okay. So now we have to calculate the AVG value. So here you see in the horizontal line, that means along the V line, the block shear portion of the plate section is both the side of the block shear portion. That means along this portion and along this portion. So we have to multiply 2 with the horizontal portion of the block shear. So from here to here, the distance of the block shear is 40 plus 60 plus 60. That means it is multiplied by 2, because here the block shear portion is provided along both the horizontal line on the upper side and also at the lower side. So that we have to multiply the 160 value with 2. If it is provided by only one portion, that means either in upper side or at bottom side, then we have to consider only 160. But in this case, the block shear portion is provided as both the sides of the V line, so that we have to multiply 2 in the total width of the block shear portion. So 2 into 160 multiplied by thickness of the block shear portion. So the thickness of the block shear portion is equal to the normal thickness of the plate section, which is given as 10. So by multiplying all these things, we got the value of the AVG as 3200 mm square. So now comes to the next area, which is AVN. So AVN is the nominal area along the V line of the block shear portion. So in this portion, we have to only deduct the bolt hole portion from the total width of the block shear portion. So we know the total width of the block shear portion is 160, and for the both side block shearing, we have to multiply 160 into 2 minus the numbers of the bolt hole portion. That means, I told you in the previous class, when we consider the half of the bolt hole portion, then we will take this portion as number 1. So here the numbers of bolt holes are here 1, again here 1, and the bottom side here 1, and again here 1. And after that, at the corner side, it is the half of the half portion. So we will take it is as 1 by 2. And another corner portion at the bottom side, here also half of the half portion of the bolt hole we have to take. So here we take the number as 1 by 2. Hence, the total number of bolt